All right. Hello, everyone. Thank you for finding the time to tune in to today's Corundum developer meeting. I'm going to go ahead and get these status updates kicked off here for 2025. All right. So briefly announcements and then the status updates. The announcements, the next developer meeting will be March 5th. Double check that's right. Yep, one month from today. The next Switch meeting will be February 12th. So if you're interested in what Carlos has been working on the Packet Switch project, um, I think the next one will be on the 12th. I guess sometimes we move those around a little bit depending on what Carlos has been working on. So
Yeah,
hopefully the
for the
next one will be
moment,
on
I
the
think
12th.
we can keep it. Yeah, for next
Yeah.
week.
All right. And then, some details about the upcoming meetings if you want to put those on a calendar. And there should be a Google Calendar linked on the wiki page. I guess I need to double check to make sure that's actually updated for 2025. That would be important, um, just in case people are actually using that. So I will take a look at that after the meeting. Okay. Now moving on to status. It's a couple different things I've been working on. I've been chipping away at the system verilog rewrite. Got to rewrite all the libraries first before working on Corundum itself, but making some progress on that. I've also been working on the DDMTD Syncy demo. I've been bouncing that back and forth between two different FPGA boards, and the performance is actually looking quite interesting at the moment. So we'll take a look at that. I actually have the demo set up right next to me here, so we can play around with that live in a few minutes. And then I also put a number of hours into working on the Alveo X3 X3522 to figure out how to get Corundum running on that. And there's some, and I got a couple slides on that because it's kind of interesting. All right, so let's go ahead and get into it. All right, so the first one is the System Verilog rewrite. And I've talked about this before. The idea is to rewrite Corundum and all the libraries in System Verilog and to switch to the CERN OHL strongly reciprocal license. And in doing so, that will mean that we'll be able to offer commercial licenses for Corundum, and then the proceeds of that will go to supporting the continued development. Hopefully, there's enough people interested that might actually be able to hire a couple people to help work on the project. But you know, gotta gotta get some income for that to work. So we'll see how that pans out. For the library porting, I've put together a new repository on GitHub. I'm calling it the Taxi Transport Library, and that's up on GitHub right now under the FPGA Ninja um, organization. So that's going to be where all of the new library code is going. And for the most part, I'm basically just taking code that I previously wrote for the existing Verilog libraries and updating it, cleaning it up, and translating it to System Verilog. So I have interfaces for AXI, AXI Stream, and AXI Lite, and I've ported a handful of modules, some primitive stuff, linear feedback shift register, generator module thing, UART, AXI Stream, and a few Ethernet components, to the point where I've been able to test a 1 gig Mac, no UDP stack, just a Mac looped back on a VC108 and a 10 gig Mac on a ZC106. And so far, that works as expected. Um, so here's a few notes. The first one is a tooling status. Icarus Verilog, unfortunately, is not usable at the moment because while you can declare interfaces, you can't actually use them because it doesn't support mod ports. So what's the point? Verilator actually seems to work fine. It works with CocoaTV. Finally, they seem to have worked out all the kinks in the integration there, and the SV interfaces also work. So and you can do it support the logic type and the always FF, always com, all of the basics in System Verilog. So that's great. And I've also been testing with Vivado. I'm not using the latest one. I'm using 2021.2. If it works using 2021.2, then I presumably it'll work with everything between then and now, right? They're not going to be removing some random feature of System Verilog, I don't think. So yeah, it's like if we test on the latest, and it works there, you don't necessarily know how far back that can go. So if everything works with Vivado from 2021, then pretty good chance that's a good subset of System Verilog to use. I've also tested it in Quartus. It builds on Quartus Prime Pro 23.1. I have not yet tested that build in the hardware, so I need to do that. That's on my to-do list. but no errors with the build process. However, it does not build on Quartus Prime Lite / standard because they support System Verilog, but it's like a really old version of it that doesn't have interfaces and doesn't have a number of other things. So that's doesn't really give you much advantage over just regular old Verilog. So I'm not sure if people are using really old devices at this point, really, what to do about that. And also, I guess the lower end ones, right? It's like Cyclone 10 GX is on Pro. The rest of Cyclone 10 is on Prime Lite. So yeah, I'm not sure what to do about that at this point. One possibility is SV to V, which can take System Verilog and convert it to Verilog. But unfortunately, there's some bugs in SV to V that need to be fixed. So first time I tried it, I ran into one issue and realized I was using an old version, updated it. That issue was fixed, but ran into a different bug. So um, I opened an issue. We'll see if that problem can be fixed. There'll probably be another one. We'll see. But hopefully, with SV to V, I'll be able to get a working design put together. So, and then hopefully the output of that will work in at least Quartus Prime Lite and Standard. It would be great if it could also work in, say, ISE, and then we could even maintain support on, 6 series devices. Because that's one of the downsides about moving over to System Verilog is, you know, it's one of the reasons I didn't want to take the existing libraries and just directly convert them, because then I'd have to remove example designs for devices that, aren't supported in ISC or whatever. But if SV2V works, then that could be useful. And the main reason I'm looking at this is I know some people, it's not so much about Corundum, but about some of the libraries. I know some of the Ethernet stuff is used on other devices, older devices, and the XFCP code I know is being used on like Max 10 devices that are targeted by Quartus Prime Lite, Quartus Prime Standard. So, maintaining that support would be good. Doesn't necessarily have to be quite as clean, but yeah, we'll see about that. I also ran into some slightly annoying quibbles with the System Verilog typing. System Verilog adds the new logic type, and I know that's purported to replace reg and wire, where you can just it basically infers the whether it's a flip-flop or just a wire based on how you use it, but it's actually not quite the case. It's not completely a drop-in replacement for, reg or wire. One obvious problem that I've seen some people complain about is that if I think it's if you declare something as logic and then you do an initializer on the same line, that's just an initializer. It's not the same as if you declare a wire and then assign it on the same line. So there's a couple of quibbles there, but the bigger issue that I ran into, so the reason it's not quite a replacement is that there's actually kind of two types in System Verilog. There's a net type and a data type, and basically you need both on a given entity, right? So wire and reg are net types. Logic is a data type. So if you declare something as logic, then it's going to be either a wire or a reg. That's determined through some other process. But the problem is that top level module ports cannot be just a bare logic. When default net type is none, which catches errors if you make a typo when making a connection or something like that, you have to also specify reg or wire. Otherwise, you get an error. And I think it's Vivado that complains about this. Maybe it was fixed in a newer version. I'm not sure, but at least on, I think, 2021.2, if you declare the module ports just bare logic, you get an error. So the first thing I did is I tried replacing all the logic with just a wire again to revert it back to what it was in previously in Verilog. But turns out Verilator doesn't like that. And if you specify the default value for unconnected input ports, well, then Verilator complains. So you have to have things declared as logic for Verilator to be happy. So the only thing you can do is declare all the module ports as wire logic, which is slightly annoying, but okay, whatever. So much for System Verilog being, less verbose. But at least that's a straightforward thing to work around. It seems like inside the actual module, it's fine to declare stuff just as logic all by itself. This only seems to be a quibble with the module input output ports for some reason. And it could be a quirk specific to Vivado. I'm not sure. But yeah, in the code base, I've done everything as wire logic. But with these modifications, then you can actually get a pretty significant improvement in how to at least glue things together with System Verilog. So just as an example, this is how you connect up the AXI stream adapter module in Verilog, right? You have to connect all these parameters. You have to connect a bunch of wires for the input and the output. It's quite a few lines of code. And with quite a few lines of code like this and a lot of, it's not exactly replication, but it sort of is, right? You open up lots of opportunities for errors and typos and mix-ups and things like that. And connecting up parameters wrong can be kind of hard to debug later on. But with System Verilog, well, the first thing you do is you define the interface, and the interface has a bunch of parameters that get connected to it when you create the interface for a particular connection. And then you just pass the interface into the module. So as you can see right here, we've got one thing on the input, one thing on the output, and there's no parameters at all passed into the module because the adapter will look at the parameters that are in the interface that get passed in. Somebody mentioned that this technique doesn't necessarily work, but it seems to be working okay in both Vivado and Quartus. So I'm not sure. And maybe Vivado at one point had problems with extracting the parameters out. But this ends up producing really clean code, and like I said, it reduces the possibility for errors because if you have to pass both the parameters and the signals down the hierarchy, there's lots of opportunities to mess something up. So with this, they're all passed down as a self-contained unit. So it should make it a lot easier to glue a bunch of pieces together at higher levels. The other thing that I've been working on, so that's about wraps it up for System Verilog. The other thing that I've been working on is the time synchronization stuff. So I've updated the 10 gig Syncy demo on the Alveo U200, and I've done a number of little things. So one of them is I tweaked the frequency, the offset frequency, and the widths of the accumulators, and I retuned the software PLL, so that the PLL locks much more reliably now, which is nice. And I reduced I guess I increased the offset frequency from an offset, n over n plus 1. Originally it was 1 part in 2 to the 16. Now it's 1 part in 2 to the 13. So that it does a couple things. One, we still have a decent phase resolution of about 1 picosecond, but you have a better pull-in frequency range where you can determine unambiguously whether one end or the other is at a higher or lower frequency. Because with the much closer spaced, 1 part in 2 to the 16, if you're on the wrong side of the offset frequency, then things get a little screwy. But by moving the offset frequency away by a couple hundred ppm, it makes the coarse locking more reliable. And it also has the advantage of producing more phase measurements per second, right? Because with the higher offset frequency, when you mix them together, you get the difference frequency is higher. So there's definitely a trade-off there. I haven't really fully explored that space yet to figure out what the most optimal value is, but this change, I think, improves things at least somewhat. But one thing I've discovered is that with the GT668 time measurement cards, I can really only get maybe 100 picoseconds peak to peak. I've not really been able to do a lot better than that. But I finally realized that if I take one output, so we're not actually time syncing, I just take the output of one FPGA, split it, and run it into 2 channels on the GT668, I also measure about 100 picoseconds, which is a bit of a head scratcher. And what I suspect is going on is that the slew rate on the I/O pin that I'm feeding into that I'm generating the 1 pulse per second signal that I'm measuring is too slow. And as a result, it only takes a little bit of noise to really move around the transition time. So that means that, some other technique needs to be used, either there needs to be some other method for getting the timing signal out of the FPGA, right? Maybe something can be done via one of the serializers or something that has a much higher slew rate. I'm looking into that. The other possibility is to try to do the measurement, directly on the FPGAs itself. I was thinking about using the GT668 mainly just have an independent measurement of, how well is this thing working. But um, with the setup, I can actually look at the phase detector output after making a complete circuit, and get an idea about the true synchronization performance. Um, and then what I can do also is add an optical delay line and see what happens, right? If I step the delay line by 10 or 20 picoseconds and then see what happens, we can get a measurement of how well this is working. So I put together this. So I got my hands on an optical delay line at JDSU HD4, which I think has 370 picoseconds delay range, something like that. It's not huge, a couple inches, I think, travel internally, but it's scriptable, and it definitely seems to get the job done. And I put together a little demo for PTTI, and we can easily discern 10 picosecond steps and probably even significantly narrower than that. So this is what the demo looks like that I put together. We got the HD4 delay line down here. I got two FPGAs here, the Alveo U200s, and then stepping the delay line in increments of 10 picoseconds. That shows up very nicely in the output of the phase detector. So just for a little zoom in, this is what it looks like when we're stepping with 1 picosecond increments, right? So this is just I have a little Python script that's driving the HD4 delay line. So we start at 0, we go -10, 0, -9, 0, -8, so on and so forth, all the way up to, +10 over here. And in the middle, you can't really differentiate, but yeah, definitely even, 4, 3, 2 picoseconds, you can definitely see it change. Now the two traces I have on here, the white one is the raw data read out of um, the status register. The red trace here is averaged. I can't remember the exact settings for that. I think it's an exponential weighted moving average over like 10 or 50 samples or something like that. So it actually does a pretty good job smoothing things out. So this looks pretty promising. There's probably still some room for improvement here. As you can see, the entire y-axis here is only about 35 picoseconds from top to bottom. So that's looking a lot better than what I was seeing with the GT668 card. And if we look at just this middle portion, ignoring the shifting around of stuff, that's only about 15 picoseconds or so peak to peak. So that's pretty good. And the idea is that this is going to be sort of the physical layer component to White Rabbit. Now, obviously, I need to do some additional higher level work as well in order to get the full protocol stack working. But this is a good starting point, at least. See, do I have anything else to say about that? Okay, yeah, I guess that's about it for now. The idea is that with the system Verilog rewrite, then I'm going to start, once I get the Mac and PCS components implemented there, then I'm going to start working on fleshing out all of the time synchronization subsystems with this higher resolution support and get that rolled into the new code base. So then once I get Corundum ported over, then we'll be able to use that and get the much higher resolution timing information. As far as how I'm going to implement White Rabbit, that kind of remains to be seen at the moment. I need to make this work at multiple link rates as well before moving ahead with the rest of the implementation. So this one is only running at 10 gig, but long term, I have some ideas for how to support multiple link rates. 1, 10, and 25 at least. 100 gig is potentially going to require some additional soft logic to extract some timing information. So that'll be a longer term thing. But yeah, with the new code base, I'm going to start cracking. I can get cracking at this as soon as I can. All right. So moving on to the Alveo X3 / that's X3522 card. So this is one that is kind of interesting because they provide actually a speed grade 3 FPGA, and they're available on eBay for only like $800 or so. And there might have been some listings for less than that, but I think these were originally designed for HFT applications or something. They have sort of a low latency network driver. I'm not super familiar with all of its capabilities. The card itself provides two DSFP slots, which is interesting. I hadn't heard of a DSFP before I got one of these cards. It's backwards compatible with SFP, but the idea is that a DSFP can provide two lanes if you have a DSFP module. And these parts actually support the GTM transceivers with PCIe 4C. So they support proper PCIe Gen 4 by 8. And I have a Corundum design put together for these. But there's a little wrinkle, right? So there's actually two variants of the X3522. There's the X3522 non-PV and the X3522 PV. What's the difference? Well, the X3522 is basically a NIC. You can only run the manufacturer's image on there. You can't modify it. Versus the X3522 is basically an Alveo board, right? It's part of the Alveo family. You can target it from Vivado without a license, as far as I'm aware. And you can load a user image on it. But apparently you can convert between the two via software. So what's the difference? Can we take, and the listings on eBay that I found so far are for the X3522s, not the PV version. So you can't, at least by default, install, your own image on there. So what is the difference, and can we convert an X3522 into an X3522 PV effectively and actually load Corundum on there? Turns out that the X3522 flash is write protected. So the QSPI flash, you can't write to it. You can load Corundum onto it via JTAG and run it, and you can read the flash, so you can access the flash, but you can't write to it. So the question becomes, well, we want to put Corundum on these permanently. Well, how do we unlock it? Now, the first thing to understand then is, how the flash is locked in the first place. So the flash it has internal protection mechanisms, and it's locked via non-volatile sector protection bits. Those bits are then locked by something called the global freeze bit, and there are a couple of OTP registers that affect how the global freeze bit works. Out of the box, when you have a new part, the global freeze bit is not locked by default. But once you set it up properly, and you blow one of the fuse bits, then the global freeze bit will be active when the part comes out of reset, and then you can't access the sector protection bits. You can unlock the global freeze bit by sending this unlock password command. You obviously can't read the password out of the flash chip once it's been programmed, but you can try as many times as you want. And the password is it's 8 bytes long. So you figure, okay, there's no way you can guess that, because 8 bytes is 128 bits. 128 bits? No, 64 bits. Yeah. So that would take a very long time to cycle through all those. So the question is, no, so that's what the password is, right? Or the password command is, right? You send the command is 29 hex, and then you can actually send it in any of the 3 modes that it supports, or that the chip supports: SPI, dual SPI, or quad SPI, and that's followed by 8 bytes of data. The password is stored in non-volatile memory inside the flash chip, but the vendor firmware obviously has to unlock the flash to update it, right? So that means the password's got to be in there somewhere. Just like any DRM scheme, the key is there. If you know where to look, you might be able to locate it. So I went on a bit of a wild goose chase to try and hunt down the password. The first thing, looked at the driver source code, because that's available, but there's not really much of anything interesting there. It's just communicating with the firmware on the card and loading stuff into memory and pointing the firmware at the in-memory blocks to tell it what to write where. But nothing about actually locking or unlocking the flash. All right, so if it's not in the driver, then that means it's got to be in the card somewhere. So there's a microcontroller on the board called the SUC, which I think is short for the system microcontroller. And then there's the NMC, which is it's a microblaze sitting on the FPGA itself. Disassembling the firmware for that has proved a bit difficult because there aren't any really good tools for disassembling microblaze assembly. And there's also some other funkiness about just how the firmware data is structured and how it gets loaded into memory. Because there is a part of the code that's, baked into the FPGA design that, you can't see very easily. Versus once the thing is running, then it reads the rest of the firmware out of the flash and then executes it from there. So, yeah, disassembling it has been we haven't made much progress on that. I suspect the password is most likely in the NMC firmware, because we can take a look at what the system controller is doing, and there doesn't seem to be anything unlock related in there. So I tried a few stupid things. I fed the whole firmware through the unlock command with various transformations and shifts and stuff, but that didn't work. But what about observing the update with a logic analyzer? If you run the update, you hook up a logic analyzer to the QSPI flash, maybe we can see the command. So I did that. That's what the setup looks like. Had to add a couple of wires onto the back of the X3522 card so we can observe, all the QSPI signals. And well, we got that. Yeah, well, okay, so we've got hex29. That's the unlock password. It's the unlock password command followed by 8 bytes, right? But if you look at it, it doesn't look very random, right? We get 78, 60, 60, 78, 78, 60, 60, 78. There's 4 7/8s, and it's obviously 4 bytes repeating twice. Does anyone remember Xilinx before they were acquired by AMD, what their stock ticker symbol was? Yeah. I think I'm going to have to change the password on my luggage. Very secure password. But now that we know that, we can take that and roll it into the firmware update software, right? The MQNIC FW, such that when you want to flash Corundum onto a board, it will automatically unlock the flash and clear all the sector protection bits. So I haven't had time to do that yet. The biggest sticking point was to figure out this code. And then yeah, I did test it. If you send that to the flash, it does clear the global freeze bit, and then you would be able to access sector protection bits. So that's on my to-do list to get that sorted out. I'm not sure if I'll get that implemented for the legacy version of Corundum, or if that'll just wait for the rewrite. But with this, then we have another potential board to run Corundum on. Because I think right now there's actually a kind of a stack of these X3522s on eBay that could be useful. The only really sticking point with the X3522s, I think, is the JTAG cable, which uses this high density edge connector. So I managed to get my hands on a proper JTAG cable, but before that, I did make a little adapter to use a regular Xilinx cable, which worked, but it's a bit fiddly. So I don't know if people are interested enough to make a little board with one of the high density connectors, then could certainly produce those for not a lot of money. I think unfortunately the connectors are like $10 each off a DigiKey or something, which is not great. And due to the way the card is built mechanically, you have to use the right angle ones. And due to the way the connectors are built, you can only solder them via reflow. So they're a little bit of a pain to work with. But it looks like these cards should be potentially a good target for Corundum. I guess another thing to mention is that because they're a -3 speed grade, the fast ones, they tend to run very hot, and they are passively cooled cards. There's no fan. So, that could be potentially a bit of an issue if you're not putting it in a proper server. So I think that about rounds out the updates that I have for today. Yeah, if anyone has any questions or comments, go ahead and fire away.
So, with the speed grade 3, how does the timing looks like? So is it hard to get timing closure or no?
Well, speed grade 3 is faster. It's the
So
fastest speed grade that's available. So it's actually easier
yeah,
to get timing closure with the -3.
yeah, right.
Yeah.
How
Um,
many SL, how many SLRs does it have? Let me check.
this is it's not a huge FPGA. I think it's just one SLR.
Ah, okay.
Yeah. It's not one of the HBM parts. It's one of the 58G series parts. Um, and it's like the smallest one. So I would have double checked the product table to see exactly where it fits versus the, normal Vertex parts. Actually, why don't I just pull it up right now? Let's see. Um, Gotta go into my Xilinx directory here. Ultra Scale Plus product table. This one? Okay. So the part on the X3522, it's the VU23P. I mean, it's when you pull it up in Vivado, it's not the VU23P, it's the X3, um but the, normal Vertex or the normal part number I believe is the VU23P. Um Let me just double check. Yeah, so it's got four of the 58G PAM4 transceivers. Yeah, okay. So it's got 2 million logic cells, 2.2 million, which puts it between a VU7P and a VU9P. So it's actually a
Hmm.
pretty good size. Um, yeah, the flip-flops as well, 2 million flip-flops. Yeah, it's actually pretty similar in size to a VU9P. I think it's one SLR, but I guess I should open it up in Vivado and double check. There anything else funky about it? Yeah. Oh, I guess there are a couple of funky things about it. It's got four of the 58G PAM4 transceivers. It's got 34 of the normal GTYs. It's got four um, of the PCIe 4C blocks. Um, but it only has two CMAX. So
Uh,
that's kind of annoying. That's more of, I think, of an issue if you're, say, running on the SN1022. Actually, I didn't mention that, but the X3 and the SN1022 are very similar boards. They have the same FPGA. Um, the board management stuff is the same. The clocking is the same. Um, Obviously, the X3 only has half of the PCIe lanes, right? It's got 8 instead of 16. And basically the X3 is taking the QSFP that's wired to the GTYs on the SN1022 and splitting that out as two DSFPs. The 58G series are not broken out. Um, I'm not sure if there's any other uh, changes or any other differences to note. Those are the main ones that I'm aware of. But yeah, it's like on the X3522, I finally found mine actually. It was missing. This one, it's got two of the QSFPs, and the idea is that one of them is only 100 gig, right? Because it goes to the GTYs. The other one can either run at 100 gig or 2 by 100 gig or 1 by 200 gig, um, because this one's driven by the
okay.
GTMs. So it would be nice if they had a couple more CMAX in here so you could run, 2 by 100 on one and 1 by 100 on the other or something. But unfortunately, it's not set up that way. Um, oh, here's the X3522 that I modified, that I added the wires to. So yeah, you get the two DSFPs there. They look just like SFPs. They're mechanically compatible with SFP. And then I got my wire hanging out there because I just kind of whacked the back of the back plate back on. There's a couple of, what are these? SSMB, I think, connectors for basically PPS in and out, timing in and out. Um, and then, 8 lanes PCI Express, and then there's a little edge connector back here for the JTAG. So they're decently nice boards, and considering there's several of them available right now, they might be um, they might be a decent board to consider using. I mean, it'd be nice if they had QSFPs, or even if they had the PAM4 series broken out in some way. But Joe Tony says, looks like you could offer for $500. Yeah, potentially. I think there's a couple different listings. So if those are interesting, snap them up before somebody else does. All right. Does anyone else have any questions or comments? Jacka says they have less DSP slices. Yeah, that's yeah, I didn't look at the whole product table here. Let's see. The 23P, it has, oh wow, yeah, okay. That is a big difference. Um, yeah, so they have 1.3 million versus on the View 9P they have, or sorry, not they have 1,300 versus on the View 9P they have 6,800. So what? That's a factor of five,
Yeah.
I guess, something like that. Factor 4 or 5. Yeah, that's a big difference. So if you're doing DSP, that's a problem. They also have less ultra RAM, right? It says 99 megabits versus 270 megabits. So that puts it actually that makes it sort of the smallest FPGA, right? So the VU3P has 90, so and 2200 DSP slices. So yeah, the View 23P is definitely more for, data transfer than DSP applications. It is annoying though that the number of ultrarams is that low. Looks like the number of block RAMs is actually similar, right? It's 75.9 megabits on the 9P versus 74.3 on the 23P. So they have a similar amount of block RAM, similar amount of distributed RAM, similar amount of logic resources, but fewer ultrarams, fewer DSP slices. Um, but they're still decent parts. Let's see here. Guess I can pull up the little demo thing just to show people what this looks like here. Let's see. Oh, Joe's got to drop. All right. See you later, Joseph. Let's see here. I'm gonna go ahead and share. Yeah, all right. Okay, so this is what the demo looks like on the software side of things. So this window over here is running the delay line, and then I've got both ends of the two U200s are here. So this one is synchronizing, and then this is the measurements from the phase detector at the master end, right? So this one is free running and then measuring the phase after it goes to the other FPGA and back. And then this graph over here is a graph from the master end of the phase. So we can zoom into this and see um, the delay line stepping. So that's what that looks like. And we can see it as the data is being collected over here too. I've been having some fun with PyQt graph now that I've discovered it, because you can use this and do real-time plotting of stuff. So yeah, as the data is being collected, you can see that this is definitely following what the delay line is doing. So it goes back to 0, and then it'll go to 9 in a few seconds here. So seems to work. Seems to work reasonably well. This has been running all night, so it hasn't budged. Let's see. So what are we talking about in terms of the spread here? This is about 50 picoseconds or so. Yeah, about 50 picoseconds, peak to peak on here. And I guess if we're just looking at the red, that's about 30, I suppose. And then 20 picoseconds worth of offsets in both directions. So, you know, that looks pretty reasonable to me. All right. So does anyone else have any questions or comments about anything, or does anybody want to discuss anything in particular?
Yeah. So roadmap of porting, right?
Yeah.
Uh, so uh, I think I can contribute as much as I can, given that, of course, I mean, cannot, but like, yeah, maybe port some part of Corundum to the SV.
Yeah, I guess we should probably discuss that offline. I got to figure out as well how
Right,
because the only way this is going to work is that if I have the copyrights for everything, or FPGA Ninja LLC has the
right,
copyrights for everything. So I got to figure out what needs to be done to set that up properly. Because if it's just me, then there's no problem. But if other
right,
people want to be involved, then there's going to have to be some paperwork.
right.
But what that is, I'm not sure. So
Hmm.
if people are interested in helping with the porting in some way, reach out to me separately, and I will look into what needs to be done for that to work. But yeah, I mean, in large part, I haven't really been asking for too much help so far because I need to figure out kind of at a what we're going to be able to do with System Verilog, and are there going to be any major roadblocks? So I got
Hmm.
to test a bunch of stuff out on multiple different tools, make sure everything works fine, figure out kind of at a high level what the syntax is and whatnot. It's slightly annoying. I've reached out a couple of times on forums to see if anybody had much in the way of issues that they'd run into in terms of what works and what doesn't work, or just general guidance, and didn't really get much of a useful response. So I've kind of been on my own trying to get things figured out. So, um, but it looks like I found a sort of a subset that works well in both Vivado and Quartus, and definitely will help a lot with the overall organization of the code. So yeah. Um, well, the other thing too is like a lot of the code that I'm working on right now is more like just taking existing code and just updating it to work in System Verilog, and adding the interfaces and whatnot, and then also going through and cleaning up all of the Verilator lint stuff, because Verilator has a very pedantic linter, which it's a little bit annoying, but I think it's more just something that you got to get used to. I mean, you can also turn it off, but it definitely will flag issues that are potentially going to be causing bugs and whatnot. But the annoying thing is that it flags things that are definitely not bugs, and then you have to try to figure out a creative way to satisfy the linter, which is can be annoying. I mean, it does give you a way to add a bunch of what are called hot comments and turn off the linter around a particular block of code, but I don't like polluting my code with that sort of thing. So yeah, um, we'll see. So I have a fair number of modules updated right now. I'm going to continue chipping away at that in terms of all of the core Ethernet stuff. I think from the standpoint of the libraries, I'm mainly just going to be looking at the basics that are needed for Corundum without adding too much additional stuff. So it's like um, and some of the modules I think definitely need a lot more reworking. So there's a few things from the AXI stream library that are a little bit wonky, and then also like the UDP stack that is not yet parameterized to support multiple data path widths. And I think there's potentially some other changes I want to make to that one. So like I'm not going to be porting that at least initially. I might port that later. Um, we'll see, but the main focus is going to be kind of the core AXI, AXI Lite, AXI Stream, and the Ethernet MAC and PCS components and that sort of stuff. And then once all that is ported, oh, and then also on the PCIe side, um, I've been doing some ruminating on that, and what I'm actually thinking about doing with Corundum is moving back to using AXI internally instead of the segmented interface that I came up with, because one, it's going to make it a lot easier to run on like Zinc and Versal type devices, and it's going to reduce the footprint hopefully, and two, I've through all the work with Carlos and developing the packet switch components, I've learned a number of additional techniques that can be used inside the FPGA fabric for handling, out of order operations and things of that nature that should make it possible to get much higher performance out of AXI inside the FPGA. So some of the issues that I was having the first time I implemented um, Corundum with AXI, I think can be addressed. Um, and also, the first time I implemented, I didn't really know what I was doing. To be honest, I'd never done anything with AXI before, or really fully appreciated some of the features that it offers. So now that I have a slightly better idea of what that's going to need, I think what my plan is going to be is to move the core of Corundum over to using AXI, and that'll be a new set of PCIe components. So it's not going to be a one-to-one transfer of those. They're basically going to be rewritten more or less from scratch to support this new setup. But the hope is that it's going to be a lot more flexible going forward. So that's the kind of stuff that I've been trying to figure out, because the more sort of planning and groundwork you can get figured out beforehand, the easier it's going to be to actually put the whole thing together. So,
And I think there are only going to be a few attempts to rewrite the whole thing.
right, yeah.
Fewer attempts, yeah.
Rewriting the whole thing, it gives you an opportunity to take what you learned from the previous iteration and apply it. Yeah, there's a lot of changes I want to make. It's not going to be just a straight port. Like the library stuff, a lot of that'll be ported, but for the core of Corundum, most of that's going to be rewritten. Also, because I want to support higher link rates. If we can support up to 400 gig, PCIe Gen 5 by 16, that sort of stuff. It's really has to be designed that way from the get-go. Otherwise, it's not going to work very well. Yeah. I guess another thing to mention as well is that there's some of the conferences I've been to recently. There's been people doing stuff with RDMA and with scheduling and whatnot. So there's a few interesting research NIC designs out there, which have some architectural features that could be quite useful in Corundum. So it's an opportunity to take a look at some of those and figure out how to potentially roll some of that functionality into Corundum. So, and then obviously all the time sync stuff too, which should be quite useful. Anyway, does anyone else have any questions or comments, or do we have anybody else new that wants to introduce themselves? I guess not. All right. Well, if I guess it's 10 a.m. now, so you've been here for an hour. If anybody else wants to discuss anything, we can do that. Otherwise, I guess we can adjourn.
From my side, nothing. I mean, just to say good work, Alex, with all that video and all the timesync stuff. I mean, starting to look very promising. Very nice graph also. So
still a lot more work to do, but
it's looking good.
It's the concept looks promising. It's now just a matter of figuring out a lot of the details. So
yeah, it's good.
So I have something to say. So recently I've been looking into measuring a round trip latency in the NIC. So basically, when I send a packet, just check a loop, like timestamp in the NIC and get it via loopback to the software.
Okay.
And after it comes back through other side, just timestamp again on the receiving side and just read it from the kernel.
Right.
I got it working with just on the socket level, like sending raw packets and get it working.
Right.
But my requirement is on the TCP side, and it seems like Linux kernel supports some of the good things, like you
Hmm.
know, like not measuring on a sync handshaking, time, just a lot of issues that could come with timestamping, hardware timestamping during the TCP. But not sure on that level how am I going to do that, because a lot of parameters that I pass now is on the socket level. Uh,
Yeah. Well, so just explain your setup again. You have one computer, or you have two computers?
so I have two computers.
Okay, you have two computers. You're sending a packet from one, it goes to the other one, does some stuff, and then comes back, and you're time
Mhm,
stamping it coming and going on that first machine.
mhm.
Okay, all right. And you want to timestamp some random TCP packet.
Not random.
Well, all right, specific TCP packet. Okay, but you
Yeah,
want to get
and
very high
also,
resolution timestamps.
yeah, also, like there is an option to give an ID such that uh, you know in the NIC what was a sequence when NIC timestamped it, and when it comes back, you can match the IDs and you can know that, okay, this particular pack, because the queuing in the NIC might change the order, and
Right.
you kind of want to know what was, because okay, let's say I sent 10 packets from the
Yeah.
or from the user space. In the NIC it might reorder,
Yeah.
and you cannot rely on the ordering that you sent to see the timestamps,
Right.
so there is a way to know the IDs through which you can know the to match the transmit and the receive timestamps.
Hmm. Okay. This is part of the Linux kernel, or this is some
Yeah.
that subsystem is not ringing any bells, but maybe that's a new thing. But yeah, what about it?
No, so ordering this figured out, things like on the, I think on the socket level, things are looking good. On the,
Yeah.
when I go to the TCP socket, not sure how do I enable that. I don't know, because I don't think I have a lower level socket access on the TCP side.
Yeah. I mean, when you insert TCP, you're not really expected to look at the packets. But you're not trying to send a packet at a specific time. You just want to timestamp both coming and
Yes,
going, right? Yeah.
yes.
Yeah, I'm not sure what the best mechanism is to handle that. Part of the problem with the way the Linux kernel is set up is there's a nice way to do receive timestamps, right? Because you get the packet and the timestamp together. With transmit, it's more complicated, right? Because you send the packet and then later you'll get the timestamp, and
Yes.
you have to be able to correlate the two. Um, and you don't really want to get that feedback for every single packet. So, like for something like PTP, it will mark the packet. It'll tell the kernel, "Hey, timestamp this. I want the hardware timestamp for this packet," and then the kernel will return it. But you don't want to get the timestamp back for every single transmit packet, because that's going to slow everything down. Especially, so the other problem that you run into as well is that the kernel doesn't necessarily even see all the packets, right? Because you have TCP segmentation offloading on the NIC. Um,
No, that is off.
well, okay, but I'm just saying with TCP segmentation offloading on the NIC, you can't see, the kernel is seeing the segments. It's not seeing the individual packets, right?
Right.
So information is going to get lost that way, no matter what. Um, yeah, so I'm not actually sure what the mechanism is for getting transmit timestamps for individual packets if you're using something like TCP, because PTP, while it does it, it's not doing TCP, it's sending individual packets. It's like with TCP, even with TCP, you're not handling individual packets, right? You're handling just a block of data that you give TCP and it
Mhm.
sends it.
Request.
So
Mhm.
what that corresponds to in packets, is determined later. And because you're not sending the packets, you don't have any information about, which individual packets are being sent and which ones you want to timestamp.
Right.
It's almost making me think that instead of trying to timestamp individual packets on the same host, it might make more sense to use a third host to capture the data and timestamp it there. I'm just not sure the best way to do that, because usually if you get something like a dual port NIC, you might have different clocks on each NIC on each port, and that would be
It might be
a
not
problem.
synced.
So, right, yeah. So you get like a well, so I guess the Mellanox NICs, the newer ones at least, can potentially be reconfigured to only have one hardware clock across the whole NIC. Um, I have not basically I have not tried to do this sort of thing myself, but it seems like maybe if you really want to get accurate timestamps, what you want to do is split it optically and then collect it on one host, right? So by splitting it optically, you need to get some sort of an optical tap or optical splitter, and then you would have 4 optical transceivers, right? 2 for the actual link, and then 2 where you're only using the receive side to capture that. That would probably be the most reliable setup for getting high resolution timestamps, because now you're getting received timestamps for everything, and that works pretty well. Wireshark can figure that out. So as long as you're not running at a really high data rate, that'll work. Unless we can somehow figure out how to do it, in hardware. They have various packet capture solutions that use hardware, but you'd probably have to do something similar, right? Because they're not really set up to act as a NIC and then capture the transmit data out of the NIC. It's more like you have a network and you set up some replicated traffic on a switch port or something, and then you can capture that. Or you use optical splitters to peel the data off and capture that. It's always something like that. So if you really want to get accurate measurements, that's probably going to be the way to go.
Right.
I actually picked up some little splitter boxes a while ago. I don't have one lying around here, but they're, I guess it's a commercial product. Let me see if I can remember what it's called. Is it this thing? It's not that. No, this is now forwarding me to some other thing. All right. It was, so I think it was either a Viavi product or they're reselling somebody else's product, or I'm not sure. Let me see here. Okay. So I think if you there's a product called the NTAP. Um, if you search for that on eBay or like if you put in like fiber NTAP, then you'll see them, and they have they have multiple splitters internally, and you can get them in both single mode and multi mode. They're just even bigger boxes you can get. It looks like some of them are available for not a lot of money, but these are kind of just totally self-contained units. So obviously you'd have to get the right optical transceivers, right? If you have single mode tap, then you'd have to get single mode transceivers to connect to it, or multi-mode tap, you need multi-mode splitters. But the idea is that if you look at, say, this one, for example, the if we look at, say, that one, it's got 1, 2, 3, 4, 5, 6, 7. It's got 9 connectors on the front. It's got 3 channels. So you've got an LC duplex in and out, and then LC duplex that is the the copies of both paths, right? So you get 2 duplex fibers and 2 simplex fibers, right? one host would go into the A port, the other host would go to the B port, and then you take two simplex fibers out of the output port, the tap port, analyzer port, whatever it's called, and then you'd run that to the receive inputs on the other two hosts.
Okay.
If that makes sense, right?
Yeah.
Or on the other two ports, and then I think ideally what you would do is put those in, I don't know, maybe a ConnectX 6 or something. I gotta see if ConnectX 5 can do the single clock thing. I'll have to look up what the command is for getting the NIC into the correct mode, so you only have a single PTP clock. But you don't need to time sync it because you don't care about the absolute time, only the relative time. And
Yes.
if you don't touch it, if you set it up to use a single clock and you don't touch it, then I think you'll be okay. I'm not 100% sure, but yeah. But yeah, that should, I think, work pretty well for what you're trying to do, and then you'll get
Okay.
the highest
Okay.
resolution that the NIC can give you in terms of the timestamps.
Okay.
And what data rate are you running at here? 10 gig, 100 gig?
100 gig.
100 gig. Okay. So 100 gig is, you're going to have to get the correct optical transceivers for that. How are you connecting it up right now? DAX?
Yeah, DAX.
Yeah. Yeah. So for 100 gig, you got to get the right optical transceivers. You can use the multi-mode ones, but the problem is the multi-mode ones tend to be like MPO fiber. So you get 4 TX and 4 RX channels, and then you need multiple taps and a whole bunch of fiber. It's a pain in the butt. So what you really want to do is get the single wavelength, or not single, but single fiber, not single fiber, the duplex LC type transceivers. So there's several different options you can use. But there's definitely a few ones you want to avoid. Like there's bidirectional transceivers. Don't get those. Yeah, you can get dual LC multi-mode, but bidirectional to use both fibers for transmit and receive. So it doesn't work for this. Probably the best one to get would be the CWDM for transceiver modules, which
Okay.
have a single wavelength transmit, single wavelength receive. And there's somebody on eBay that has like 10,000 of them or something for like a couple of bucks a pop. I bought like 50 of them from the dude a while ago, so I got a whole stack of those. I guess I don't have a free one lying on my desk right at the moment, but yeah, there's several companies that made them, and they are dirt cheap. There's also a related module called the DR1, I think, which also does something similar. But in that it's duplex LC, but the DR1 is a single wavelength. It's got more stuff going on inside the module in terms of PCS layer things. So it's like the DR1 can only run at 100 gig, but the CWDM4, it's 4 separate channels all the way through. So you could run 4 separate links. You could run them some at 10 gig, some at 25 gig, potentially even run them at 1 gig. I mean, you get a lot more flexibility with that. So probably the most straightforward thing to do is get a couple of the CWDM4 modules, get some fiber, get one of these tap boxes, and then you should be good to go.
So then I will be measuring, I'll be just using a NIC to capture the traffic, and
Yeah.
I'll be time stamping on both sides on the TX and just taking a relative measure, right?
Yeah,
Or
exactly.
okay. Okay,
That's
that
probably going
seems
to get you the highest accuracy.
yeah, I agree.
And the other advantage of doing something like that is now you're not even affecting the computers under test, right? So it's completely
Right.
separate, right? So it's like this can be a problem. Like you don't even have to turn segmentation offloading off if you want, right? Because that'll slow things down. But with this kind of a setup, doesn't matter. Now you
Right.
might need to turn segmentation offloading off on the host that's collecting the timestamp information. Otherwise, it's not going to work very well, and you'll lose the timestamps. But yeah, depending on what you're trying to do, I think this is going to be this is going to be the highest performance method.
Mhm.
Depending on how accurate you want the timestamps, you might actually need to go like measure out the amount of fiber and say, okay, well, the delay is X over here and it's Y over here, that you can compensate for that.
No, 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 no. I don't think I'm on that level yet. It's just
Yet,
that,
right. Yeah,
yeah, it's just that I think while we are measuring on the NIC,
yeah,
we are using some sort of Go script, not some sort of Go script. We are using a Go script with a TCP library and things like that, and then we are doing a closed loop testing. The thing
right.
is, the variance on that is very unreliable and something that is, after giving a lot of thought, is not probably not making a lot of sense.
Well, maybe it is making sense. The one thing I will say is that Linux tends to give you software timestamps on transmit and hardware timestamps on receive. And that's definitely going to give you all sorts of weird behavior
Uh,
if you're not using the right timestamps. So
right.
so I'm not sure if you've verified that you're actually getting hardware timestamps in the transmit direction. But yeah, that
On the
tends to be a problem.
on the sockets I did, but yeah, I need to check with my total experimentation and things like
Yeah,
that. I think now I understand. Like previously, I had a very weak understanding of how timestamps used to work because the hard TX timestamp is a bit tricky because when you send it, it gets timestamp in the NIC and then it pushes to a error queue. It seems,
exactly. Yeah.
and then you read that error queue depending on when it's queues up in that particular queue.
Mm-hmm.
Uh, you kind of have to read it and get the timestamp.
Right. And you got to request on specific packets when you want the timestamp because it's not everything that's timestamped.
So
So,
I installed a package called hardware control some package. I think it's a Linux package, and I just timestamped it for, I guess, the whole, because I'm not. It is using IOCTL, and it I think timestamps the total packet that is going through the NIC.
right.
And so I no longer enable it in my C code to specifically enable the timestamp. So no IOCTL in the C code.
Hmm.
Just globally enabled it.
Yeah. Well, I mean, I think using this totally
Yeah,
separate setup is going to be much more reliable. So,
yeah,
yeah, you got to buy a couple of bits and pieces. But honestly, it's not that expensive to get one of these taps and a few transceivers.
yeah,
Like if you put in CWDM4, yeah, I think you'll see what I mean about these things being dirt cheap.
yeah. You can
Um,
check.
yeah. AOI CWDM4, $3. So yeah, those are probably going to be the way to go. Plus you'll need some fiber. So if you want to double check on whether you're getting all the right parts, feel free to ask me on Zulip or whatever.
Sure.
Carlos has a whole setup over there with fiber and and optical switches as well. I don't know about splitters, but we definitely went over that whole shebang to make sure we had all the right fiber and the right transceivers and whatnot.
Yeah, yeah. I mean, getting everything from eBay, I think is the cheapest way to
I
go.
mean, when they're asking $3 per transceiver, that's like,
Yeah.
like,
Take
yeah,
it.
give me like 10, get a few extras.
Yeah.
Yeah, cheaper than a coffee, I guess.
It's
Almost.
insane. Yeah. Yeah, get a few extras and then take one apart and see if you can figure out how it works. Some of these things are actually pretty cool inside and how they're built. So
Yeah.
Right.
one of the transceivers that I took apart two different CWDM4 transceivers and they had completely different internal construction. One of them was using free space optics and one of them was using like an AWG on a glass substrate. I'm like, well, that's wacky. Um, but yeah, they're pretty cool. They can
Yeah.
really cram a lot of stuff into a very small package.
Uh, so, by the way, at some point I sent you a link over Zulip regarding this particular optical based company which is making interconnect, I guess. Not an interconnect. I think, yeah, kind of. They're working on optical interconnect between the CPU and the whole NIC
Oh,
and
yeah, there's a
things like
bunch of
that.
companies doing
Yeah,
like that.
yeah.
But
Later, I figured out there are a bunch of
they're not going to
companies.
go anywhere. Anyway, what about it?
Yeah. So I think I think you are pretty experienced in optical and optical signaling and stuff like that. What's your comment about it?
Ah, well, some companies like don't provide any technical information whatsoever in their on their website. So I think that one is one of the worst examples of that, where it doesn't really tell you anything about what they're doing. So yeah, I hate that kind of sales brochure. It's like, okay, so you're doing something with optics. I guess that's nice. What are you doing? Like, yeah, okay, great. Yes, I don't know. I don't know what they're doing. Is it good? Is it bad? I mean, I don't know. Does it have, you know, promise in the future of doing something? I mean, I guess they seem to think it does. If they're getting investors, they must have been able to convince somebody to give them money. But yeah, I don't know. If they don't post very much technical information about what they're doing, then I can't really say much. Well, I mean, is there a reason you're asking about that particular company? Is you just found it and it looked interesting, or?
No, yeah, it just looked pretty interesting. I think there is a particular group in MIT which is working on this sort of things, and people graduated from that group and opened individual companies.
Oh, okay.
There are two such people I know. They graduated from the same group and they opened
Gotcha.
companies on similar stuff.
All right. Well, if there's nothing else that we want to talk about, then I guess we can go ahead and close this down for now. We'll see you guys next week, I think, for the Switch meeting, right?
Yep.
Yeah.
Next week.
All right. Sounds good.
Right.
Talk to
See
Thanks for
you.
the meeting.
Thanks for the meeting.
See you.